voltage, or electromotive force. We're going to start with electric potential energy. We'll have two positive charges, one over here, one over here. They're initially at rest. We could also use negative charges, but hey, we had to pick one. In order to move little q, and typically this means that's a smaller charge, to big Q, we need a force opposite to the Coulomb repulsive force. If you remember from the last unit, like charges repel. So to get little q near big Q, we have to exert an external force. So if we exert this force over displacement, that gives us work. Work is being done on the system. That work will increase the energy of the two-charge system. And once again, we're going to use an analogy to gravity. Just like raising an object above the floor by a force puts energy into the object floor system, we're doing the same thing here with electric potential energy. And back when we were dealing with gravity and position, it was called gravitational potential energy. The energy of the system of two charges is called electric potential energy. And it's equal to this equation here, and R is the distance between the two charges. Notice the similarity of that to the electric field and the electric force, except we have an R there instead of R squared. Also, going forward, instead of calling it EPE, which could also be elastic potential energy, we'll use the more conventional U that represents potential energy. Not sure why. Well, probably because P stands for power. And we'll put a subscript here for E, for electric potential energy. This tells you how much energy is stored in a system of charges and is now available to return that energy in a different form, such as kinetic energy. We will now define electric potential, V, or more commonly known as voltage. Yes, and this is the same voltage you see on batteries. That will be the electric potential energy per charge, or U sub E divided by Q, or you can just rearrange the algebra and have UE equals QV. The unit of voltage is the volt, or joules per coulomb. And a way to interpret that is you have a 9-volt battery here, let's say you have one, that will add 9 joules of energy to every single coulomb of charge that passes through it. Now the coulomb's rather large, so typically we're going to be dealing with millicoulombs or microcoulombs. So in that case, you'd have let's say a millijoule of energy for every millicoulomb of charge that passes through the battery. Batteries, which we just discussed on the previous slide, they're a source of electric potential, or voltage, and they use chemical reactions to separate the charges and then put the electrons in motion, which will then move through circuits and power things like light bulbs, machines, vacuum cleaners. What we have there is chemical energy being converted into electrical energy. Both of these batteries over here are 1.5-volt batteries. Every electron that leaves the battery has the exact same energy. The larger battery, the AA, it still has the same voltage, but it has more chemicals for reactions, so it will last longer than the AAA. That's the only difference, plus it's bigger. The voltage supplied by an ideal battery, that's a battery without any resistance, without any age problems, it's just a perfect battery, that's called EMF, or electromotive force. Don't worry about it so much right now. I just wanted to put the name out there because we'll be using it. It will be discussed in greater detail in AP Physics 2. So let's switch instead of electric potential, and we'll talk about voltage. That's more commonly known to people who aren't taking physics classes. And that electrical energy, which is measured by voltage, is carried by the moving charges and is used by various circuit elements. Now what are those? We'll get into that later, but one example is a light bulb. Right? You plug a light bulb into a light fixture, you plug that into the wall, and you have current flowing through that. Okay, those are charges. The light bulb will convert the electrical energy into heat and light energy, which will decrease the energy of these charges that are flowing through the circuit, and will also decrease their voltage after they pass through the light bulb. We have a couple different ways of saying that. One is 5 volts are dropped across the light bulb, or there's a voltage drop of 5 volts across the light bulb, or, to get really fancy, there's an electric potential difference of 5 volts across the light bulb. And what's happening there is energy is being converted from electrical energy to thermal energy and light, or motion if you're powering a vacuum cleaner. An important circuit element that we haven't talked about yet is the resistor, and that will be covered in this chapter right here that's coming up soon.